Content-based recommendations used embedding spaces for items only, whereas now, for collaborative filtering, we are learning where users and items fit within a common embedding space along dimensions they have in common. We can choose a number of dimensions to represent them in, either using human-derived features or using latent features that are under the hood of our preferences, which we will learn how to find very soon. Each item has a vector within this embedding space that describes the item's amount of expression of each dimension. Each user also has a vector within this embedding space that describes how strong their preference is for each dimension. For now, let's keep things simple and keep things just one dimension looking at items, and we'll get back to multidimensional embeddings later and how users fit in. We'll start simple and then build ourselves up. We could organize items, let's say movies, by similarity in one dimension, for example, of where they fall on the spectrum of movies for children to movies for adults. Let's say we have the movie Shrek. We want to know where it falls on this children to adult movie spectrum. Using our own built-up knowledge, we would say that Shrek would probably go to the far left, because it's an animated movie mainly for children. What about the movie The Dark Knight Rises? Where do we think it goes along our axis? Well, The Dark Knight Rises, we know, is definitely a more adult movie than Shrek, so it should go to the right of Shrek on the spectrum. Now that we have two movies placed, things start to get a bit harder because we have three choices to decide from. Here we have Harry Potter that we want to place along our spectrum. Does it go to the left of Shrek, to the right of The Dark Knight Rises, or somewhere in between? From our internal representations of these movies, we can guess that Harry Potter goes between Shrek and The Dark Knight Rises. It definitely has more adult themes than Shrek, but still not as much violence or adult themes as The Dark Knight Rises. Exactly where in between it should go, we will get to soon. All right, 3 movies placed, more to go. We now have 4 choices of where to place the movie Memento. What to do? Memento has some very adult themes, and our knowledge would probably place it even farther right than The Dark Knight Rises. Lastly, we want to place the triplets of Belleville. As you can see, every time we add a movie, the number of positions we can place it in relative to the other movies increases by 1. Imagine if we had thousands and thousands of movies. The triplets of Belleville is pretty far along the children's movie scale, but not quite as much as Shrek. So this is where we will put it. However, this is all very qualitative, with just some unknown relative position along a number line. Can we make this a little more quantitative, maybe with some numbers? We've now added values on where we think these movies lie along our number line. High negative values are considered very much children's movies, and high positive values are considered very adult. Movies close to 0 are basically halfway between what we'd say is a very childish and very adult. We've essentially created a 1D embedding space with our coordinate system, and our 5 points could have these values, indicating where they sit on the children's movie, adult movie spectrum. Now, you can calculate similarities via distance metrics between the points in our coordinate system. Those that are closer or have a smaller distance are more similar, at least with respect to this children-adult factor we chose. Based on these values along this axis, The Dark Knight Rises and Memento are the most similar movies. However, even if 2 movies are very close in this one-dimensional projection using child-adult spectrum, and other projections using other features of the movies, they could be extremely far apart. Let's now add a second dimension to calculate similarities between movies. For example, where movies fall on the art house blockbuster spectrum. Not only have we arranged the movies along the children-adult movie spectrum, they are now spread out along the second dimension. As we add dimensions, our embedding spaces grow exponentially larger and become sparser and sparser with large voids between points in the embedding space. In this 2D embedding space coordinate system we created, our 5 points could have these values indicating where they sit on both the children's movie, adult movie spectrum and the art house blockbuster spectrums. As we can see, the movie's points in our 2-dimensional embedding space have the same coordinate values as along our original children-adult spectrum. However, they have now been spread out along our new art house blockbuster spectrum. The points haven't changed at all, but our coordinate system has. Coordinate systems aren't important. They are just a way to describe points within space. Based on these values in our new 2-dimensional embedding space, The Dark Knight Rises and Memento are no longer the closest, or most similar movies, at least not using the dot product distance metric. The 2 closest are now Harry Potter and Shrek. In fact, our previous closest aren't now even the second closest, which goes to Harry Potter and The Dark Knight Rises. This is due to how close these three movies are along the blockbuster axis, which is dominating in the dot product calculation. So how do we apply these embeddings to the user-item interaction matrix so that we can infer how unknown interactions may be rated? Well, we've already talked about the item embeddings based on the two dimensions that we chose, children, adult, and art house blockbuster spectrums. But what about the user embeddings? Let's say we knew where a user could be placed along both of our dimensions, giving us their coordinate values in our embedding space. Each user would have a two-dimensional coordinate, and each item would also have a two-dimensional coordinate within our space. To find out the interaction value between users and items, we simply take the dot product between each user-item pair. The ijth interaction value is the inner product of the ith user vector and the jth item vector. Let's see how that looks in our embedding space. Going back to our coordinate system plot from before, we have our movies plotted in the two-dimensional embedding space at their coordinate values based on where they fall within the two factors we chose. We've also now added the users at their respective coordinates. So, what should we recommend to each user? Let's look at the leftmost user. To find the answer to what movie the leftmost user should watch, all we need to do is take the dot product between the user and each movie. In this example, we chose to return the top two highest movies, which end up being Shrek and the Triplets of Belleville, because they had the two highest dot products for that user across all the other movies. Now, this might seem obvious from looking at this graph. However, it is not as easy for a computer to see this, because our trained eyes and the neural networks in our brains have had decades of experience to see. Yet, this is only with two dimensions and with few items. If we were to increase the dimensionality, we humans would have a very difficult time discerning which movies are the closest. We would probably stop inspecting and just take the dot product. The same can be done for items. Let's say we want to see what movies closest to Shrek are. Instead of taking the dot product between a user and all the items, we take an item of interest and take the dot product with all the other items. In this example, we once again are returning the top two, which turns out to be Harry Potter and the Triplets of Belleville. You can do the exact same to find users similar to a user of interest by taking the dot product between users. So, as we can see, users and items can be represented as d-dimensional points within an embedding space. In our example, we chose some human experience-based factors for each of our two dimensions, and humans manually scored each movie, giving it a value for each dimension along its axis. We did the same for evaluating each user's coordinates in our embedding space. Well, this works great for toy examples with 4 users and 5 items, but it quickly becomes unscalable as more users and items are added to the system. Furthermore, as we saw in the last course, when psychologists used what they thought would be good features for embeddings, it turned out not to be that great. Here, our human-derived features may not be the best choice. So, how can we choose then? Fortunately for us, the embeddings can be learned from data. Instead of defining the factors that we will assign values along our coordinate system, we will use the user-item interaction data to learn the latent factors that best factorize the user-item interaction matrix into a user factor embedding and item factor embedding. We are essentially compressing the data, our very sparse interaction matrix, and relying on the generalities within, which are the latent factors. You might be reminded of PCA, SVD, or other dimensionality reduction techniques, like we covered in the last course, for reusable embeddings. The user interaction matrix factorization splits this very large user-by-item matrix into 2 smaller matrices of row factors, which are users in this case, and column factors, which are movies in this case. You can think of these 2 factor matrices as essentially user and item embeddings. Now, you might be wondering why matrix U has 2 columns and matrix V has 2 rows. Well, this is simply the dimensionality of our learned embedding space of our latent features. Remember, a latent feature is a feature that we are not directly observing or defining, but are instead inferring through our model from the other variables that are directly observed, namely the user-item interaction pairs. Just like for other dimensionality reduction techniques like PCA and SVD, the number of latent features is a hyperparameter that we can use as a knob for the trade-off between more information compression and more reconstruction error from our approximated matrices. Just how much space are we saving? Let's say there are U users and I items, which gives our user-item interaction matrix A a size of U by I. If our website has 50 million users and 10,000 movies, that's already 500 billion interaction pairs. On the other hand, if we can have k latent features, then U will be U by k elements, and V will have k by I elements. The total space is just the number of users plus the number of movies times the number of latent features. Even with 10 latent features in this case, it is still 1,000 times less space than before. As long as the number of latent features is less than half the harmonic mean of the number of users and the number of items, this will save space. For this hypothetical website, that would be almost 10,000 latent features, 9,998 to be precise, which is almost as if we hadn't embedded the movies at all, since there were 10,000 movies to begin with. Each movie is essentially its own feature. To make a prediction, we simply take the dot product of a user with the item factors, or an item with the user factors, and we will get a prediction value for that particular rating. In this example, we want to predict the rating for user 4 for the movie Shrek, which is the third column. So we multiply 0.1 with 1 and 1 with a -1 to get a value of -0.9. Harry Potter gets a prediction of -0.11, and the triplets of Belleville also gets a prediction of a -0.9. If we were recommending the highest predicted unwatched movie to user 4 out of the movies shown, then it would be Harry Potter because it has the highest predicted score. Now it's time to test your knowledge about finding the best recommendations based on user and item similarities. Based on this user-item interaction matrix of users and movies, which movie should user 4 watch? The correct answer is A. To find this answer, we should have calculated all the dot products between user 4's user factor vector and all the movie factor vectors. User 4's predicted rating for Harry Potter by the dot product is a -0.11. The triplets of Belleville and Shrek are both a -0.9. Their Dark Knight Rises is 1, and Memento is 0.91. Remember, we are just recommending the top 1 movies in this question, so we should return the max dot product between user 4's user factor vector of 0.1 and 1 with all the movie factor vectors. So, why is the answer Harry Potter when the Dark Knight Rises has the highest dot product out of all the movies? The reason is because the user has already rated the Dark Knight Rises implicitly in this example, and thus we don't want to recommend that the user watch a movie they've already seen, because most users know whether they like something in the past and instead want to watch something new. Therefore, we must filter out all the movies that have already been rated, and then, from the resulting subset, choose the top 1. This results in Harry Potter, although with a negative dot product, which means that the movie is predicted to be below neutral sentiment, but has the highest dot product value out of the unwatched movies.